with 2.8, the derivative as a function. Okay, so the derivative can be considered as a function, and then the values represent the slope of the original function. And then this is probably the best formula for finding the derivative directly using the definition. This is probably the one that's the easiest because it allows you to keep x as a variable and then let h go to 0. Okay, and another way to think about it is if you think of taking the derivative as being a capital D, that would be the operation of taking a derivative. It's going to take some function to its derivative, okay? So in reality, you can think of the derivative as a function itself, or taking the derivative as a function itself, and the elements that operates on, and the domain is the set of functions that are differentiable, and then the range are their derivatives, okay? So that's one way to think about it. And then, of course, you can also think of taking derivatives at specific points. But this one, we're going to concentrate on the derivative as a function. Okay, so let's move along right here. So here we have a graph, and we're supposed to estimate the value of each derivative. Okay, so let's start with this first one, f prime of -3. So what you do is you come over here to -3, and then you come out here to this curve, and you look at the tangent to that curve. Okay, and you think, what is the slope of that tangent? Well, I guess you could start here and go to here. It looks like we went down by, or maybe I'm a little off. Maybe it's more like this. Maybe I didn't draw that wood. In which case it would be here and here. So we went down by 1.5 and went across by a little bit more than 1.5. So if you went down by, if we did go down by 1.5 and we went across by 1.5, then the slope is going to be, okay, the slope is the rise over the run. So that would be -1.5 over 1.5. That would be -1. Okay, and so I think that actually, -1 works when you put it in as an answer. But -1.1 also works. There's other values that can work. Okay, let's do this one right here. So let's say, okay, that could be -1.1, or -1 would be fine too. They give you a little bit of leeway. Okay, so let's take a look at this one, f prime of -2. So -2 is right here. So you come down to there, and it looks like it's horizontal. Okay, it looks like horizontal. So that looks like the derivative is going to be 0. Okay, f prime of -1, and that wasn't too bad. When it's 0, then that's not too bad. So -1. So you come back here to -1, and that's this point right here. And you try to like look at what this curve is here. So we went from here to here as we went over by 1. So it went up by maybe, I don't know, it went up by maybe a half. Yeah, maybe a half from there to there. So, and then across by, it went up by half as we go from here to here, and by about a half, and it went across by 1. So we can try 1/2 for that one. Okay, f prime of 0, that would be right here, and that one, let's the slope right there. So let's see here. It went from here to here. I want to cross by 1 and up by maybe 1. So that would be 1, okay? So if that's going to be, if that's 1 over 1, it went up by 1 and across by 1. Or maybe across by a little bit, maybe up by a little bit more than 1, so maybe 1.2. Okay, so let's try 1.2. Because from here to here, that's a little bit more than 1. So going up by 1 would put us about right there. That's a little bit more. Okay, so you just kind of have to estimate these. F prime of 1. So here's 1 right here, and we're looking right there. And that looks pretty steep right there. I mean, that looks pretty much follows the curve. So if we go from there to there, we're pretty much in the middle there, So it went across by 1 and up by 1, 2, maybe 2.5. Let's see if 2.5 works. That seems to work. Now, some of these are off, so you might have a different impression of what they are, but that's fine. F prime of 2. Okay, good. That's an easy one. 2 is right there, and it looks like we're at a horizontal tangent, so that's going to be 0. And so that was good. Yay, that was the only easy one. Okay, F prime of 3. So here we are at 3. And so we're at this point there. And it looks like follows that. Okay, so as we go from there to there, we went down by, it looks like we want to cross by 1, okay? And went down by about 1.3 maybe, 1.4. So negative 1.3, because we went down. Let's see if that works. Okay, those values seem to work. Okay, now what we're supposed to do is we're supposed to graph the derivative. So this function, well, you can't really see the function anymore. Oh well, but you can see these values here. So this function has a derivative, and the derivative is apparently is one of these functions here. So what you have to look for is you want f prime of negative 3 to be negative 1, and that appears to be the case. Okay, so that's good, and right there that's okay. And these ones should be here and here, so they're not. So that means that these two, neither of those could be it. Okay, the next thing you want to look at is this one right here. F prime of negative 2 has to be 0. Okay, so it has to go through there, and those do. These two also, but they're already disqualified. The next one would be this green one, 1/2. So f prime of negative 1 has to be 1/2. And that's good. But this is negative 1/2, so that's not good. Okay, so that's no good. And then we can like continue to go with these other ones. F prime of 0 has to be about 1.2. They got it like I got about 1.5. Wow, looks like we were way off. And then f of 1 is about 2.5. Ooh, they have it at 3. Whoa. And f prime of 2 is 0. F prime of 3 is negative 1.3. Okay, so I don't agree with this part right here. It doesn't seem to follow what's going on, but we'll just roll with it. And this has got to be the answer, this first one. Okay, let's look at number 2. The graphs of 4 derivatives are given below. Match the graph of each function, a through d, with the graph of its derivative. So these are functions, and these are derivatives. Okay, so let's look at this one here first. And some things to note is that the derivative is 0 here and here. So that means we look for something where the derivative is 0 at both of those places. This function will do it. This function does it. This one doesn't, because maybe here and here, but then I've got this other 0 in the middle, but the derivative is not 0 there. Okay, so this is really the only function that can work for A. So that's got to be 2. Okay, and again, it's the derivatives are 0 there. We can look at the other stuff. So the derivative is negative here, and you can see the function is below the x-axis, so that means it's negative. Derivative is negative, it's because it's decreasing. It's increasing here, so the derivative is positive. So it's positive here, and then decreasing here, that means the derivative is negative again, so negative down below the axis. Okay, so this is 2. Okay, now let's look at this one right here. So here, this is kind of interesting because this is a kind of a line segment or array. Another line segment in the middle and another line segment here. And when you have a line segment, the derivative is constant there. So it's a constant. So it's something like this. So this part right here is like that. Okay, and then this part here is like this one is positive. And then here the derivative is negative, which is right here. So you got a negative slope here, so the derivative is negative. Derivatives aren't going to exist where you have these kind of cusps. Okay, the derivative is just not going to exist. Okay, so here, derivative does not exist. Okay, because the limit, as if you come along this way, you're going to get this value here, whatever it is. And if you come this way, you're going to get this value here, whatever it is. And so it just doesn't. So that the difference quotient, the limit does not exist. Okay, so you can tell in the graph when you have these cusps or sharp points, then the derivative is not going to exist. The function can still be continuous there, but the derivative doesn't exist. Okay, so this is going to be number 4. Okay, now moving along, let's look at this one right here. So here we have the derivative is negative here. It's 0, and then it's positive. So negative, 0, positive. So it looks like this is the this is the derivative of that. Okay, so it's going to be 1. And then finally, I guess we only have 1 left. So this last one has got to be 3. But let's try to explain why. So the derivative is 0 here, here, and here. And so the function is 0 there, there, and there. Okay, and increasing here, which means you're above the x-axis. Decreasing there, which means you're below the x-axis. Increasing here, which means above, and then decreasing, which means you're below. Okay, so move on to the next one. Okay, so here what we're supposed to do, use estimates of the derivative to sketch the graph of f prime on the same coordinate axis. Okay, so let's see here. The derivative is negative here, and the slope gets steeper and steeper and steeper. So here the slope was not that bad, but as you get, and so maybe it's like right here, but as you get closer to here, the slope's gonna go like that. Okay. Over here, the slope is positive. Here, the slope is negative, so it's all below the x-axis. Here, we're positive, so we're above the x-axis, and it's really steep. So it's going to come down like that. So you're going to get something like this, which is this one, this first one. You're basically going to get this first one. Okay. So let's go to this next one, number 4. A rechargeable battery is plugged into a charger. The graph C of t shows the percentage of full capacity that the battery reaches as a function of time t elapsed in hours. Okay, so the battery charges pretty quickly in the beginning when it's empty, but then when it starts to fill up and it's getting like completely full, then it takes less time. Then it takes more time to charge that last little bit. Okay, the rate of charging is going down. Okay, so what is the meaning of the derivative C prime of t? Okay, this is going to be the rate of change, the rate that is charging. Okay, so the rate of so that would be, let me see, instantaneous rate of change of percentage of full capacity with respect to elapsed time in hours. So it would be this first one. Okay, the second one is elapsed time in hours required for a given percentage. No, average? No. So C prime is instantaneous, it's not average. Okay, so derivatives are instantaneous, they're not average. They're not averages. Okay, so the slope of the secant line would be an example of being an average. Okay, but the derivative is the slope of the tangent line, so that's instantaneous. And then this last one doesn't make any sense. Okay, so there's more questions, there's more part to this. So remember this, the next part, sketch the graph of C prime of t. Okay, so let's go back and look at this. Okay, so here, this is pretty steep right here. So that means that if we were to sketch the graph over here, by the side, that means that right here it's really steep and it's positive. So that means you're going to be up here. And then as you come down, you're getting you're getting smaller, smaller, smaller right here. Okay, so it's going to be like this is what the graph's going to look like. So that will be this first one here. Okay, so what does the graph tell you? Okay, the graph tells us that the rate of change of percentage is decreasing without bound. Okay, without bound would mean that it just keeps going decreasing and going into the negatives. But this is clearly bounded, okay? So so that without bound is wrong. Okay, the graph tells us that the rate of change of percentage of full capacity is increasing. No, that's not increasing. The rate of change is decreasing. Decreasing and approaching 0. Okay, so it looks like this one maybe. Okay, the graph tells us the rate of change is increasing and without, no, it's not even increasing and it's not without bound. Just the rate of change is increasing and no. Okay. Okay, so now we get to, hopefully we get to the fun part. Find the derivative of the function f of x equals mx plus b using the definition of derivative. State the domains of the function and its derivative. Okay, so this is just a linear function, and a line has a constant slope. So before we even do this, you could determine that the derivative is just going to be m. It's going to be the slope. Okay, but let's go ahead and use the formula. Okay, so f of x plus h is what we want to put right here. I'm just using this. Okay, so that means m. So I replace every x with an x plus h. Okay, so this x gets replaced with an x plus h. Okay, that's this piece. This piece is just the original function, mx plus b. Okay, and then of course I'm dividing by h. So pay attention. This is what you do. You plug in. You change. Replace this x with an x plus h, and that goes, all the x's over here are replaced with x plus h's, and they go right here, this first spot. Then you subtract just the original, and then you divide by h. You're just plugging everything into the formula. That's all we're doing. Okay, now let's go ahead and distribute everything. So mx plus mh plus b, and then we have minus mx minus b over h. Okay, now, generally, at this point, you're going to get a lot of things cancel out. If you don't have a lot of cancellations, then you might be doing it wrong. Okay, lots of stuff canceled out. And then finally, these h's, with all that gone, oh, dang it. I forgot to put the limit of h coefficient. I forgot to put this limit piece here. Okay, now with everything gone, then the h's reduce. Okay, and you just get m as your answer. Okay, and this happens everywhere. There was no problem, so the domain is negative infinity to infinity, and the domain of f prime is also negative infinity to infinity. Because there's no problem anywhere taking the derivative, and there's no problem with plugging any x's into here. Okay, let's do another one. This one's a little bit more difficult. We'll give us some more practice. So you want to find the derivative of this function using the definition of derivative. And when I say the domains of the function and its derivative. Okay, so this is g. Okay, now I have the formula here. Oh, this should be a t. Oops. So I have the formula, but I replaced the x's with t's. And it's just the same thing. It doesn't really matter what variable you use. Okay, so f of t plus h, which would be g of well, maybe I should I'll just copy the formula down here. Okay. Okay, so let's go this one first. Okay, so for that one, you want to plug a t plus h in here in place of t. Okay. Okay, and then you subtract, and then this piece is just going to be that f5 over the square root of t. And then, of course, the h just carries through. Okay, so you want to be very careful about plugging these things in. Here, everywhere over here, you replace the t's with t plus h's. Over here, it's just copy this down right there. Okay, now, and again, I forgot the limit. Okay. Okay, now, this time you're going to have to do some manipulation. But in the end, you need to manipulate it so you can reduce these h's. Because as h goes to 0, this is 5 over root t minus 5 over root t. That's 0. And this is also 0 as h goes to 0. So you have a 0 in the denominator. So you have to resolve that somehow. And what you can do is you can multiply each of these. So take the first one, multiply it by the square root of t over the square root of t. So multiplying it by a fancy form of 1. This is all this, the blue one. Okay, and then this one, I'll be clear. We're going to multiply by the square root of t plus h over the square root of t plus h. So this is just getting a common denominator. Okay. So it's just getting a common denominator. Okay, and then after you do that, then what you can do is you can combine these two together. So you have 5 root t minus 5 root t plus h over h times the square root of t plus h times the square root of t. Like that. And well, that didn't help much. Okay, so now what we're going to do now is we're going to multiply by 5. Yeah, okay, we're going to factor 5 out. Let's go. Let me go ahead and do that right here. Factor to 5 out. Okay, so now what I'm going to do is I'm going to multiply by the square root of t plus the square root of t plus h over itself. Okay, just like that. Okay, and then so then what happens there is the numerator becomes, because this is the square root of t minus the square root of t plus h times the square root of t plus the square root of t plus h, then the numerator becomes this times this, which is this squared, which is t, minus this squared, which is t plus h. And then of course here we have h times the square root of t plus h, the square root of t, and then the square root of t plus the square root of t plus h. Okay, so what happens is this and this are going to reduce, and you're going to have, in the numerator, you're going to have a negative 5h. Over h times the square root of t plus h, square root of t, the square root of t plus the square root of t plus h. You can have that, okay? And then, of course, these h's are going to reduce. Okay, so that's, you should always get the h's to reduce. If you're doing it right, that's pretty much always going to happen. As far as I can tell, that should happen. Okay, now, hold on a second. Hold on. I'm just going to take the limit because we're running out of space. So basically, at this point, you can just plug in h equals 0. Okay, so plugging in h equals 0 gives you the square root of t here, and this is also square root of t, and then this is the square root of t plus the square root of t. So that's negative 5 over, this one combines to be t. So 2t root t. So this right here is 2 root t. This right here is t. So that should work. Yeah, so that's the derivative. And the last part is the domain of the function. Well, you can have it, what you need t greater than 0 in order for that to work. So from 0 to infinity is going to be the answer there. And then also for the derivative, you can't have t being 0, you can't have it negative either. Okay, so those are the domains there. Okay, let's move along to number 7. Okay, the graph of f is given. State the numbers at which f is not differentiable. Okay, there's actually 3 things to look for here, or a number of things. Okay, so main things though. where you have cusps or sharp points on the graph. Okay, so that would be this right here. That's a cusp or sharp point. Okay, so that would be one case. Another case where it's not differentiable would be where it's not continuous. So if the function is not continuous, then it's not differentiable. And this is the case right here. Okay, as you're coming in from the left, you get a different, or you're coming in from the left, you get a different limit than coming in from the right. So it's not continuous. It can't be differentiable if that's the case. Okay, so that would be 0. And you're interested in where this happens. So -4 and 0 is where this happens. -4 is where this happens. It's not the y value, it's the x value. And then another one would be where you've got a vertical slope. And that would be something like this right here. Okay. So 2. Okay, so at those points, it's not differentiable. Okay, so -4, 0, and 2. Those are a few examples. Now, of course, if the function is not defined, then it can't be differentiable either. But that's yeah. Now, if you go and study the theory of a derivative and everything, then you can get some weird things that are actually differentiable, or weird things that are continuous but not differentiable. Okay, so anyways, let's see here, number 8. Okay, so here we have 3 functions, A, B, and C, and one of them is the original, another one is the first derivative and of the original, and then the third one is the second derivative of the original. And we're supposed to try to figure out which one is which. So a good place to look at would be to say, hey, where? Okay, so if A was original, then its derivative would be 0, maybe right here. So you can try to argue that way. And yeah, the B has a derivative that's 0 right there. So A could be the original. Maybe A is the original. That was quick. And if B is the second function, then B has a 0 right here, right? And or B, the derivative is 0 here, which means C could be it. Wow, interesting. And B is pretty flat. B's probably got a 0 derivative here as well somewhere, so I know it's the case. So maybe A is the original, B and C. But let's see if there was another possibility. Could C be the original? Or okay, so if C has a horizontal tangent here, so the derivative is 0. But neither A nor B have intersect the x-axis right there. Okay, so C can't be it. So where it has a horizontal tangent, the derivative has to intersect the x-axis because the derivative is 0. So it has to intersect there, but neither A or B does. So that means that C has to be that one. And then likewise, B has a horizontal tangent here. So that means that if A were its derivative, A would have to intersect the x-axis here, but it doesn't. C does. So C is the derivative. So C is the derivative of B. Okay, so that's pretty much the order right there.